Reinforcement learning, RL, is a branch of machine learning focused on training agents to make sequences of decisions by interacting with an environment. Unlike supervised learning, RL does not rely on labeled datasets, but learns through rewards and penalties, promoting autonomous decision-making. Its foundation is rooted in behavioral psychology, inspired by how humans and animals learn from experience. Let's break down the core components of reinforcement learning. At the heart of it all is the agent, the decision-maker, the learner. It's the agent that takes actions based on the current situation, or state, of the environment. The environment is the world the agent interacts with, and it provides feedback in the form of rewards. Positive rewards encourage the agent to repeat certain actions, while negative rewards discourage them. The agent's behavior is defined by its policy, a kind of map that links states to actions. This policy can be deterministic, always choosing the same action in a given state, or stochastic, choosing actions with different probabilities. To make good decisions, the agent needs to estimate the long-term consequences of its actions. That's where the value function comes in. It estimates the total expected reward the agent can get from a given state, following a specific policy. A related concept is the Q function, which estimates the expected reward of taking a particular action in a given state and then following a policy. Finally, there's the discount factor. This determines how much the agent values future rewards compared to immediate ones. A discount factor close to 1 means the agent cares a lot about long-term gains, while a value closer to 0 makes it more focused on immediate gratification. Let's explore the different learning paradigms in reinforcement learning. There are two main approaches, model-free and model-based. Model-free RL relies solely on interacting with the environment. It doesn't build a model of how the environment works. It learns by trial and error. Q-learning and SARSA are examples of model-free methods. Model-based RL, on the other hand, builds a model of the environment to predict what will happen when the agent takes certain actions. Planning algorithms like DynaQ fall into this category. Now let's dive into some key algorithms. Q-learning is a popular model-free algorithm. It updates what's called a Q-value, which represents the expected reward for taking a specific action in a given state. It's an off-policy algorithm, meaning it learns the optimal policy regardless of what the agent is currently doing. SARSA is similar to Q-learning, but is on-policy, meaning it evaluates the policy the agent is actually following. Policy gradient methods take a different approach. They directly optimize the policy to maximize expected rewards, and they're especially useful for situations with continuous action spaces. Finally, deep Q networks, or DQNs, combine Q-learning with deep learning. They use neural networks to approximate Q values, enabling them to handle complex problems with huge state action spaces. DQNs also use techniques like experience replay and target networks to stabilize the training process. Reinforcement learning is finding applications in a wide range of fields. Gaming is a natural fit, and RL has achieved superhuman performance in complex games like chess, Go, and various video games, with notable examples like AlphaGo and AlphaStar. In robotics, RL enables robots to learn complex tasks, such as walking, grasping, and navigation, paving the way for more sophisticated robotic arms in manufacturing. Autonomous vehicles are another exciting area. RL is used for path planning, obstacle avoidance, and decision-making in self-driving cars. In healthcare, RL offers the potential to optimize treatment strategies, accelerate drug discovery, and enable personalized medicine. For example, RL models can be used to optimize radiation therapy schedules. The financial world is also embracing RL for portfolio optimization, algorithmic trading, and risk management. Even energy management can benefit from RL, optimizing energy consumption in smart grids and HVAC systems. Reinforcement learning maximizes rewards through agent-environment interaction. Key algorithms like Q-learning and policy gradients drive its diverse applications. Challenges remain, but RL offers immense potential for optimal decision-making.